Hello. So this is kind of to start us thinking about radicals and what radicals are, and then do a little bit of work with them. So if you remember, radicals can be described as roots and cube roots, or a root of some kind. And so you guys know the square root of 4 is just asking what times itself equals 4, and we know it's 2 because 2 times 2 is 4, and the same thing with the square root of 64. Now we say square root because if I had a square, for example, with an area of 4 square inches, we would know that each side was 2 inches in length, because to find the area of a square, you go, side times side. And so the square root makes a lot of sense if you're trying to figure out what the side lengths of a square are. And that might be one way to help us think about why are they called square roots. Well, it's really, in this context, a square side. If the area is 4, what's the side? Well, it's 2, because 2 times 2 is 4. Same thing with the 64 here. And then the cube's a little bit different. With a cube, you actually could think about it as a cube, and I'm not the best artist in the world, but if you had a cube and you wanted to know the volume, if you knew the volume of the cube was 27, so if all the space inside there was 27 cubic inches, you would know that one side of the cube was 3. Because to find the volume of a cube, you know its length times width times height, or side, 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 because they're all the same. And so that's the cubic root. Well, so in general, this little number right here, whatever it is, I've expressed it with n. That's basically asking the question. This whole thing is asking the question. There's some number out there. What is that number? That times itself n times equals x. And so that's the idea of a radical. Now that we kind of reviewed the idea of a radical, let's get down to the actual skills that we need for this first lesson. So the first thing we got to know how to do is evaluate perfect roots. So we're looking for, in this first example, what number times itself 4 times equals 16. And it turns out that 2 does, because 2 times 2 times 2 times 2 is 16. We end up with 4 times 4. Whoops, that's not a 4, that's a V. Let me fix that. 4 times 4 equaling 16. So we know that. So what times itself equals 16? Now, notice I paid attention to this little 4 up here. That told me that I needed that number 4 times, whatever that number was. Well, if there is no number up here, it defaults with a 2. We always assume there's a 2 there if there's nothing written. And so this is, of course, 4, because 4 times 4 is 16. And I want to emphasize something. The answer to this problem, the answer to the fourth root of 16 is not 2 times 2 times 2. It's 2. So this is not actually the answer. The answer is just simply 2. Just how I wouldn't say that the answer to this is 4 times 4, I would say it's 4. But the answer is 4 because 4 times 4 equals 16. So I kind of actually made a mistake when I said that equaled 2 times 2 times 2 times 2. Shouldn't have written it quite like that. So we know this one is 6. And of course, this one is 5, because 5 times 5 times 5 is 125. All right, that's the easy part. Let's move on to some new stuff. So what about estimating roots? So this right here, there's no number times itself that exactly equals 19, no whole number, no integer. And this is actually something that we call irrational. This is an irrational number because if you were to try to figure out what times itself equaled 19, it would have a bunch of decimal places off to infinity that never repeat. So it's a lot like pi. But pi is 3.1415 and so on forever, and there's no repetition, there's no real pattern to the digits. Well, same thing with roots of non-perfect square numbers or non-perfect cubic numbers, whatever root you're trying to take of a number that's non-perfect. So if this is the square root of 16, we know 4 times 4 is 16. So if we're going to estimate this, if we want to be able to estimate this in our head, and maybe even a little bit on paper, we would want to think, what's the perfect root just less than this, and what's the perfect root just more? So I know 16 is a perfect square root, just less than, and I know, let me get rid of this, and I know that the root just more than is 25, the perfect number, I should say, perfect root. So this we know is 4, and this we know is 5. And by default, we absolutely know that the square root of 19 then must be between 4 and 5. There's no way around that. And so here's an interesting thing. Something you might want to think about is how close is 19 to 16? Well, these numbers are just 3 apart, right? So there's a difference of 3 between the 16 and the 19. And the 19 has a difference from 25 of 6. So these are actually 6 apart. And so when you ask yourself, is my square root of 19 going to be closer to 4 or to 5? You're going to end up being closer to 4 because 19 is closer to 16 than to 25. So when we estimate square roots, it'd be nice if we could get something close to, I don't know, the nearest 10th, for example. So how are we going to do this? Well, once we've identified that it's closer to 16 than to 25, one method is to actually start guessing and checking. So it's going to be 4 point something. Let's try 4.3. Let's square 4.3 and see what it comes out to. So 4.3 times 4.3 is 18.49. That's pretty darn close to 19. So let's try 4.4 now. 4.4 times 4.4 is 19.36. So hey, we know that our root of 19 is somewhere in between 4.3 and 4.4. We have estimated this good enough by hand. And if you need any more accurate, then you should use a calculator, right? And so another possible way to go about this is to say, okay, I'm going to just estimate that it's right around 4.35 because that's between 4.3 and 4.4 somewhere. It actually is pretty close to 4.35. It's actually 4.358898944 and so on forever. So it's a pretty good way of estimating. Let's do one more example. So in this problem, let's just go through the process one more time. I'm going to find my perfect root just less than 30, my perfect square root just more than 30. We'll go ahead and write those numbers down, the actual roots of those. And then I'm going to find the differences. So this is 5 away, but 6 away over here. So I know my root's going to be between, of 30, my square root of 30 is going to be between 5 and 6. And so if our root's between 5 and 6, I know it's going to be 5 point something, right? And it's a little tiny bit closer to 25 than it is to 6, but it's almost right in the middle. I mean, 30 is right in the middle of 25 and 36, almost right in the middle. So let's try 5.5 to start. Could 5.5 be pretty close to the root of 30? Well, the way to tell is, of course, to multiply it by itself and see if you get anything close to 30. Turns out that's 30.25, so that's pretty close. What about, let's go down a little bit. Let's see what 5.4 times 5.4 is. Well, that comes out to 29.16. So I know the root of 30, the square root of 30, is somewhere between 5.5 and 5.4. So when I'm estimating this, I could say this. I could say the square root of 30 is approximately 5.45. Or you could just say 5.4. The reason I said 5.45 is because I know that's a number right in between this. And I'm not all that accurate. I'm actually only accurate to the nearest 10th in this situation. And that's really all we need to be able to do by hand. If we need anything more, we'll just use a calculator. So in your homework, I'm actually asking you to do a few of these, to actually estimate a few of these and try to get to the nearest 10th if you can. All right, let's look at one more thing that has to do with radicals. So we can simplify roots, but to do this, we've got to understand that roots are just exponents. So the square root of x is the same thing as x to the 1/2 power. And we can actually simplify that and say, okay, we know there's not always a 2 here because it's not shown. But there is in this case, and then there's a 2 here. There's actually a pattern that's going on. So we can actually make this property out of it. We're going to discuss this property in much more detail and why it works in class. And so, of course, this translates to the cubic root of 27 is the same thing as 27 to the 1/3 power, which is the same thing as 3. Okay, but because they're exponents, that means that they're governed by the same rules that we just learned about that govern exponents. We're going to use that to simplify these things. So, what does that mean? Well, it means that, like, for example, the square root of 8 is the same thing as the square root of 2 times the square root of 4. Because 8 to the 1/2 power will be the same thing as 2 to the 1/2 times 4 to the 1/2. And we're going to explore this in much more depth in class. Right now I'm asking you to look for the pattern and practice a few problems to get fluent. We're going to look at the y in class. And so you might notice right away that this is not a perfect square. That's a square root of 2. That's an irrational number. But this is a perfect square. the square root of 4 is just 2. So to simplify this, we're actually going to write it as 2 square roots of 2. Where, and I'll color code this for you, I got that reddish looking 2 from this part of the problem. So take whatever you're being asked to simplify, break it into either a perfect square if it's asking us for a square root, but if it's asking us for a cubic root, break it into, a perfect cube and try to pull one out. They won't always be simplifiable or be able to be simplified, but some of them are. Let's look at one more example. So this is the last slide here, and you guys have hung in there. I know this is a longer video than normal, cram-packed with information. But if we're going to simplify these radicals, the first thing we should look at, oh, you know what, I forgot in my example, I'm supposed to write that there. There we go. The first thing we should look at is, what's the root? So this is a square root, this is a cubic root. So let's take the square root for a minute and forget about this cubic root just for a second. Can we break 20 into something times a perfect square? And I want a perfect square because it's a square root. In other words, can I say that this is the same thing as the square root of 4 times the square root of 5? Well, sure, because we learned that you can do that on the last slide. We learned that the square root of 5 times the square root of 4 is the square root of 20. So, with that being said, this now is a perfect square. So this becomes really 2 times the square root of 5, or 2 square roots of 5. And that's how we would finally simplify this. That's how we would write it. However, I want to point something out here. I want to point out that we could have tried to break this up into the square root of 2 times the square root of 10. But that wouldn't have got us a perfect square. So when you're breaking these up, try to look for that perfect number that you can simplify into an integer. Okay, let's take a look at this cubic one. I'm looking for a perfect cube. Let's think about some of the perfect cubic numbers we know of. I know 8 is 2 times 2 times 2. I know 27 is 3 times 3 times 3. So if you're just like laying in bed at night bored, start thinking about your perfect squares and your perfect cubes because they're going to help you. I know 4 gets a little bit higher. So let's think. Can I break 54 into 8 and something, into 27 and something maybe? Well, as it turns out, this is the same thing as the square root of 27 times the square root of 2, because 27 times 2 is 54. And so, oh, I'm saying this wrong. Let me say that differently. This is the same thing as the cubic root of 27 times the cubic root of 2, because the cubic root of 27 times the cubic root of 2 is a cubic root of 54. That's a mouthful. But now I know that this is just going to be 3, because 3 times 3 times 3 is 27. So I'm going to simplify this down to 3 cubic roots of 2. And this, my friends, is equivalent to the cubic root of 54. These mean exactly the same thing. And if you were to type these into a calculator, they will give you the exact same decimal. Same with these over here. The square root of 20 is exactly the same thing as 2 times the square root of 5. And so you might wonder, why do we care about simplifying these? Well, we're actually pulling out as many normal numbers as we can and leaving as few irrational parts as possible. We're also going to talk about why we care about that in class. So you're probably going to have a lot of questions after seeing this video. Do me a favor, write those down, don't lose them. Try your best on those problems on the website. See if you can't replicate this a few times, and then come into class with those questions and let's figure out why all this stuff works. Thanks for watching.